Hello everyone. In our previous class, I have explained you about the electric potential at a point, okay, due to the conducting charge sphere. Now in this class, I will explain you the electric potential due to the non-conducting sphere or insulating sphere at different points. Suppose this is a non-conducting sphere or insulating sphere. Okay, we have to derive the expressions for the electrostatic potential at different points. At a point outside the sphere, on the surface of the sphere, and inside the sphere. Okay, and for that we must know about the values of electric field which we have derived earlier. Okay, now let's recall those values of electric field at different points. Electric field outside the sphere. I am writing E naught means electric field outside of the sphere. That is how much? KQ upon R square R cap. Where R means this is the point where we have to derive the expression for electrostatic potential. Okay, and we have placed the test charge here. We are bringing the test charge from infinity to this point. Okay, that is the amount of work done is known as your electric potential. This point is at a distance of small r from the center of the sphere. Okay, so now ES means electric field on the surface of the sphere is how much? KQ upon R square R cap, where capital R is the radius of the sphere. EI means electric field inside the sphere is how much? KQ upon RQ R vector. Q means the total charge distributed to the sphere. Okay, what is the difference between conducting sphere and non-conducting sphere? Okay, in previous class also I had explained you. Now also once again I am recalling it, that in case of your conducting sphere, the charge resides on the surface of the sphere, whereas in case of your non-conducting sphere, the charge is distributed throughout the sphere. Now by using these values, we can derive the potential at outside the sphere, on the surface of the sphere, and inside the sphere. Case 1, point is outside the sphere. Now if the point is outside the sphere, then small r is greater than capital R. By the definition of potential, I know V0. V0 means potential at outside. And how much? Negative integral of E naught vector dot dr vector. Okay. Now we will put the value of E naught. E naught is how much? KQ upon R square R cap dot dr vector. Now look, potential at P, that means what? We are bringing the test charge from infinity to P, means infinity to R distance. So here the limit will be infinity to R. Infinity to R. Now, how much? Minus KQ taking outside of the integration, it will be how much? 1 upon R square R cap dot dr vector infinity to R. Now, what is the value of r cap dot dr vector? R cap dot dr vector. A dot b, we know A dot b equal to A b cos theta. Look here, r cap and dr vector are along the same direction. So angle between them is 0 degree. Now magnitude of r cap is 1. Magnitude of dr vector is dr cos 0. So cos 0 is 1. Now it will be how much? Dr. Put the value here. So it will be minus kq 1 upon r square dr infinity to r. Okay. Minus kq 1 upon r square dr integration means r to the power minus 2 dr integration. So it will be how much? R to the power minus 2 plus 1 upon minus 2 plus 1 infinity to r. Minus kq r to the power minus 1 upon minus 1 infinity to r. Minus minus will be plus. So kq r to the power minus 1 means 1 upon r infinity to r. Kq, put the upper limit here, 1 upon r minus, put the lower limit, so 1 upon infinity. 1 upon infinity means is 0, so it will be how much? Kq upon r. Okay, so potential at a point outside the sphere, okay, outside of the non-conducting sphere is how much? Kq upon r. Point is on the surface of the sphere. If the point P is on the surface of the sphere, that means this point will be at this point. Okay, that means this r, small r, will be this one, means small r will be equal to capital R in this case. Small r will be capital R. Okay, that means we have to determine the potential at this point. That means we have to bring the test charge from infinity to this point. Okay. So by the definition, we can write Vs means potential on the surface. Will how much? Negative integral of Es dot dr vector. Limit will be infinity to capital R. Es kq upon r square r cap dot dr vector infinity to r. So this will be how much? If you follow the same procedure as we have done in case 1, you will get kq upon r. Okay, so potential on the surface of the non-conducting sphere is how much? Kq upon capital R. Okay, so conclude that the potential at a point outside of the sphere and on the sphere, on the surface of the sphere, are same for both non-conducting and conducting sphere. Okay. Case 3. Point is inside. Suppose the point is inside the sphere. Means we have to bring the test charge from infinity to this point, which is at a distance of smaller, okay, from the midpoint, from the center of the sphere. Now, in this case, small r is lesser than capital R. Okay. Look here, we have to bring the charge from infinity to this point. That means here two situations are arising. Number one, infinity to R, capital R, means on the surface. Okay. And case 2, situation 2, from capital R to small r. Okay. Infinity to capital R, then again capital R to small r. Okay. So potential inside the sphere will be how much? Negative integral of E outside dot dr vector from infinity to capital R plus from capital R to small r minus integration of here electric field inside the sphere, and you know inside the non-conducting sphere there is the electric field. Okay, it is E inside dot dr vector, limit is from capital R to small r. Look, this value we have already derived in a previous case. Its value is kq upon capital R. Directly I am writing. Now here plus into minus, so it will be minus integration E inside. E inside is how much? kq upon rq smaller vector dot dr vector from capital R to small r. Okay. Look, r vector dot dr vector. R vector dot dr vector is how much? Both r vector and dr vector are acting along same direction, so angle between them is 0 degree. Now A dot B equals to AB cos theta. So here magnitude of r vector means r, magnitude of dr vector is dr cos 0 degree. Cos 0 is 1, so it will be how much? R dr kq upon r minus kq upon rq. Its value is r dr capital R to small r. kq upon r minus, taking common, kq upon rq, because r is also constant. R is the radius of the sphere, that is constant, that is fixed value, so we can take outside of the integration r dr capital R to small r. It will be how much? kq upon r minus kq upon rq. Now r dr integration is how much? r to the power 1 plus 1 upon 1 plus 1 r to smaller. kq upon r minus kq upon rq. It is 2 taking outside, so r to the power 2 r 2 smaller is how much? kq upon r minus kq upon 2rq. Use the values, r square minus r square. Okay. In common, kq upon r. Okay. Here 1 minus 1 upon 2 r square minus capital R square. So it will how much? kq upon r. This is how much? Take the LCM, 2r square will be 2r square minus r square minus capital R square. That will be how much? kq upon 2rq 2r square minus r square plus capital R square. kq upon 2rq, 2r square plus r square is 3r square minus small r square. V inside. This is the expression for potential inside the sphere. Okay. Now we have derived the expression for potential inside the sphere, that is kq upon 2rq 3 r square capital R square minus small r square. So by using this value we can derive the expression for the potential at the center. Okay. Suppose that is VC. VC means at the center. Okay. Potential at the center. Potential at the center. Center means this R will be 0. Okay. So if we put the value of R is 0, then we can get the value of VC. Okay. So VC will be how much? KQ upon 2RQ 3R square minus 0. Okay. How much? It will be KQ upon 2RQ into 3R square. So potential at the center will be how much? R square, R left, then 3 by 2 KQ upon R. Okay. Now KQ upon R is the potential on the surface of the sphere. We have derived this expression. Okay. So we can write 3 upon 2. This is Vs, potential on the surface of the sphere. That means, look here, potential at the center of the sphere is 3 by 2 times that means 1.5 times the potential on the surface. Clear? Potential at the center of the sphere is 1.5 times that of the potential on the surface. Clear? Now we have derived the expressions for all the potentials at different points. Okay. Potential at a point outside is how much? kq upon small r. Potential on the surface is how much? kq upon capital R. Potential inside the sphere is how much? kq upon 2rq 3 r square minus small r square. Potential at the center of the sphere is how much? It's 3 by 2 kq upon r. That means 1.5 times that of the potential on the surface of the sphere. Okay. Now by using these values, okay, we can plot a graph in between potential versus distance. If we plot a graph in between V versus R, okay, by taking these values, then we may plot a graph. What type of graph will be obtained? Look, this is O. O is the center of the sphere and R is the radius. Okay. Now on the surface of the sphere, the value is Vs. Vs is the potential on the surface. On the surface means at R. Okay. And at the center, the value is 1.5 times that of Vs. 1.5 times means the value will be here. Okay. This is Vc. This is 1.5 times that of Vs. Look, we conclude that the potential at the center is 1.5 times that of the potential on the surface. That means while we are moving from the center towards the surface, the value of potential goes on decreasing. Then the graph will be like this. Again, from the surface, when we are moving outward, means the value of small r is increasing, then the potential is gradually decreasing. Here, what is the potential? Is V outside, that is how much? kq on r. Okay, this value, the potential goes on decreasing, and such type of graph will be obtained because V0 means potential and the outside is inversely proportional to the distance. If the distance will increase, then the potential will decrease. Okay, then such type of graph will be obtained. Thank you.